Welcome! In this session, we'll explore problem number 1269, number of ways to stay in the same place after some steps. This intriguing problem challenges us to calculate how many ways we can stay at index 0 after a given number of steps, leveraging concepts from dynamic programming. Let's dive in and uncover the solution together. The problem starts by describing the setup. You are given two inputs, steps and ARR_len. The steps variable represents the number of steps you can take, and ARR_len refers to the length of a zero-indexed array that spans from index 0 to ARR_len 1. You begin at index 0, and with each step, you can choose to move one step to the left, one step to the right, or stay in the same position. However, you must ensure that you stay within the array bounds, meaning you cannot move to indices less than 0 or greater than or equal to ARR_len. The goal is to calculate the number of distinct ways to return to index 0 after exactly steps. Since the result can be very large, the answer should be computed modulo 10 to the power of 9 plus 7. The problem also specifies the constraints for the input. Steps is at most 500, and ARR_len can go up to 10 to the power of 6. The output of the problem is a single integer that represents the number of ways to stay at index 0 after exactly steps, modulo 10 to the power of 9 plus 7. To help understand this better, consider the first example. Here, steps is 3, and ARR_len is 2. The output is 4, meaning there are 4 distinct ways to stay at index 0 after 3 steps. The first possibility is to simply stay in place for all 3 steps, which can be represented as stay. The second possible sequence for the first example is to move right in the first step, move left in the second step, and then stay in the third step. This is represented as right, left, stay. Similarly, another valid sequence is to move left first, then move right, and finally stay, which is written as left, right, stay. Finally, the fourth possibility involves alternating movements, move right, then right again, and finally left. This ensures you return to index 0 after all steps. For the second example, where steps is 2 and ARR_len is 4, there are only 2 ways to stay at index 0, either by staying in place for both steps, stay, or by moving right in the first step and left in the second, right, left. In the third example, steps is 4 and ARR_len is 2. The output here is 8, meaning there are 8 distinct ways to stay at index 0 after 4 steps. This example illustrates how the number of possible paths increases as the number of steps grows. The constraints of the problem are also important to note. The value of steps is between 1 and 500, and the value of ARR_len is between 1 and 10 to the power of 6. The problem guarantees that the result will always fit within a 32-bit signed integer, so we don't need to worry about integer overflows. However, we must ensure that calculations account for the modulo operation to keep intermediate results manageable. There are some additional edge cases that are important to consider. If steps is 1, the only valid moves are either to stay in place or move to index 1, provided that ARR_len is greater than 1. Similarly, if ARR_len is 1, the only option is to stay in place, since moving left or right would go out of bounds. Another key observation is that the range of indices you can reach is limited by the smaller of steps and ARR_len. For example, if steps is 5 and ARR_len is 2, you can only move between index 0 and index 1, as moving further would exceed the array bounds. Finally, because the result must be returned modulo 10 to the power of 9 plus 7, it is important to ensure that all intermediate calculations also use the modulo operation to prevent overflow and ensure correctness. To start, let's consider the brute force approach. The problem requires determining the number of ways to stay at index 0 after a specific number of steps. A straightforward but naive method is to simulate all possible movements for each step. At each step, if you're at index I, you can make one of 3 moves: go left to I1, go right to I plus 1, or stay at I. However, there are constraints. If you're at index 0, you can't move left, and if you're at the farthest valid index, which is determined by ARR_len 1, you can't move right. Using recursion, we can explore all possible paths step by step, and in the end, count the paths that lead back to index 0 after all the steps are taken. While this approach is conceptually simple, it has significant drawbacks. The time complexity grows exponentially, as there are 3 choices per step, leading to 3 steps time. Additionally, the recursion depth leads to a space complexity of steps. This makes the approach computationally expensive and unsuitable for large inputs. Now, to address the inefficiency of the brute force method, we turn to dynamic programming. This approach leverages the observation that the problem contains overlapping subproblems. Specifically, the number of ways to stay at index I after S steps depends on the ways to reach indices I1, I, and I plus 1 after S1 steps. Additionally, the range of indices we need to consider is limited to min steps rlen 1, because taking steps cannot extend beyond this range. To formalize this, we define dp s I as the number of ways to be at index I after S steps. The recurrence relation is straightforward. dp s I equals the sum of dp s1 I1 dp s1 I and dp s1 I plus 1. The base case is that there's exactly one way to be at index 0 with 0 steps, so dp 0 0 equals 1, while dp 0 I is 0 for all other indices I. Using a 2D table, we can iteratively compute dp s I for all steps and valid indices. This eliminates redundant calculations, drastically improving the time complexity to O steps asterisk min steps rlen. However, the space complexity remains O steps asterisk min steps rlen due to the dp table, which can still be problematic for large inputs. To further improve the space efficiency, we can optimize the dynamic programming approach by reducing the 2D table to a single 1D array. Notice that to calculate the current state dp s I, we only need the values from the previous step, dp s1. This means we can reuse the same array, overwriting it iteratively as we compute the values for the current step. This optimization reduces the space complexity from O steps asterisk min steps rlen to O min steps rlen without affecting the time complexity, which remains O steps asterisk min steps rlen. Additionally, there are some key insights that help us here. First, the range of indices we need to consider is always constrained to min steps rlen 1. Second, dynamic programming allows us to avoid redundant calculations by reusing results from earlier steps. Finally, the realization that we only need the previous row to compute the current row is what enables this space optimization. With these observations, the space-optimized DP approach emerges as the best choice, balancing clarity, correctness, and efficiency. Every approach comes with its trade-offs. The brute force method, while intuitive and easy to implement, is computationally infeasible for large inputs due to its exponential time complexity. Using a full 2D dynamic programming table simplifies the implementation and avoids redundant calculations, but it has high memory usage, which can be a limiting factor for large constraints. The space-optimized DP approach, on the other hand, achieves the best balance. While slightly more complex in implementation, it significantly reduces memory usage without compromising time efficiency. The final implementation based on this strategy ensures that the solution is scalable, correct, and efficient within the given constraints. By leveraging dynamic programming and space optimization, we address both the computational and memory challenges of the original problem, making this approach the most practical choice for real-world use cases. The problem we're solving is about finding the number of ways to stay at index 0 after a given number of steps. At each step, you have 3 possible moves: you can go left, go right, or stay in the same position. However, there's a key constraint: you can't go out of bounds. To approach this, we'll use dynamic programming. First, we define our state. Let dp s I represent the number of ways to be at index I after taking s steps. Our ultimate goal is to compute dp steps 0, the number of ways to be at index 0 after all the steps are taken. Next, we consider the base case. At step 0, the only index you can be at is 0, so dp 0 0 equals 1. For any other index I not equal to 0, dp 0 I equals 0, because it's impossible to reach those indices without taking any steps. Now, let's move on to the transition relation. At any step s in index I, the number of ways to reach I can be calculated by considering 3 possibilities. First, you might have come from the left, which is represented by dp s1 I1. Second, you might have stayed at the same index, which is dp s1 I. And third, you might have come from the right, which is dp s1 I plus 1. Adding these 3 values gives us dp s I. However, we must account for boundary conditions. If I1 is out of bounds, we ignore dp s1 I1. Similarly, if I plus 1 is out of bounds, we ignore dp s1 I plus 1. Additionally, we need to manage bounds effectively. If the number of steps exceeds the size of the array, we can limit the problem to the minimum of steps and the array size, as you can't move beyond the array's maximum bounds. This optimization helps ensure we don't waste computation on unreachable indices. To implement this iteratively, we initialize a 2D array dp with dimensions, steps plus 1, max underscore index plus 1. First, we set dp 0, 0 equals 1, as that's our base case. For all other indices I, set dp 0, I equals 0. Then, for each step s from 1 to the total number of steps, we iterate through all possible indices I. For each index, we calculate dp s I using the transition relation we discussed, while ensuring out-of-bound indices are skipped. The final result will be stored in dp steps 0, which is what we're trying to compute. To optimize space usage, we can reduce the space complexity from O steps asterisk max underscore index to O max underscore index by maintaining just two 1D arrays, one to store the results of the previous step and another for the current step. After processing each step, we update the previous array to match the current one. There are several key insights to note here. First, the bounds of reachable indices shrink as the number of steps decreases. If the array size is larger than the number of steps, the effective bounds are determined by the number of steps. Second, the problem exhibits symmetry. For example, the number of ways to reach index I is the same as the number of ways to reach index I. This symmetry can be useful for debugging and validating results. Lastly, the space-saving optimization we discussed earlier, storing only 2 rows of the DP table instead of the entire table, not only simplifies the implementation but significantly reduces memory usage. In terms of data structures, we use either a full dynamic programming table for clarity and completeness or the optimized 1D arrays for efficiency. Finally, let's analyze the complexity of our approach. The time complexity is O steps asterisk max underscore index, as we compute each state dp s I exactly once, and there are steps multiplied by max underscore index such states. For space complexity, the full 2D dp table uses O steps asterisk max underscore index. However, with the space optimization, we bring this down to O max underscore index, since we only store the results for the current and previous steps. To illustrate how this works, consider an example where steps is 3 and max underscore index is 2. We initialize dp such that dp 0, 0 equals 1 and all other dp 0, I equals 0. For step 1, we compute dp 1, I for each I. For instance, dp 1, 0 equals the sum of dp 0, 1, dp 0, 0, and dp 0, 1, which evaluates to 0 plus 1 plus 0 is equal to 1. Similarly, compute dp 1, 1, and dp 1, 2. Repeat this process for step 2 and step 3. The final output will be the value stored in dp 3, 0. This Python implementation solves LeetCode problem number 1269 using dynamic programming to calculate the number of ways to stay at index 0 after a given number of steps. Let's break it down. 1. Constants initialization. We define a modulus mod equals 10 to the power of 9 plus 7 to prevent overflow during computations, as the result can grow very large. 2. Range limitation. The maximum position maxpos we need to consider is the smaller of steps ////2, because at most you can move half the steps in one direction, and arrlen 1, the maximum valid index in the array. 3. dp initialization. We create a dp array of size maxpos plus 1, initialized with zeros. dp 0 equals 1 because we start at index 0. For dynamic programming loop, for each step, we calculate a new dp array, new underscore dp. For each position POS, the number of ways to reach it is the sum of ways to stay at POS, move left from POS plus 1, or move right from POS 1. Boundary checks ensure we don't access out-of-bounds indices. After computing new underscore dp for the current step, we update dp to new underscore dp. 5. The final result, after all steps, dp 0, contains the number of ways to stay at index 0. This approach is efficient because we only compute values for positions within maxpos, significantly reducing the space and computation overhead. The overall time complexity is O, steps asterisk min, steps, rlen, and space complexity is O, min, steps, rlen. Here, we begin the Java implementation of the solution. The method numberWays takes in two parameters, the number of steps and the length of the array. We define a constant mod with the value 10 to the power of 9 plus 7, which ensures our calculations stay within bounds when working with large numbers. Next, we calculate the maxPos, which denotes the furthest position we need to consider. This is determined by the smaller of half the steps or the array length minus 1. This optimization helps limit the computation to only relevant positions. We then initialize a DP array to store the number of ways to reach each position at the current step, and set DP 0 to 1 since we always start at position 0. Now, for each step, we create a new array new DP to store the updated counts for the next step. Inside the nested loop, we iterate through all positions up to maxPos. For each position, we calculate the number of ways to stay at the same position, move left, or move right, updating new DP accordingly. We ensure that all updates are taken modulo mod to prevent overflow. Once the inner loop has processed all positions, we update the DP array to be the same as new DP, effectively moving to the next step. After processing all the steps, the total number of ways to stay at position 0 is stored in DP 0, so we return it as the result. This approach ensures that we efficiently compute the solution by leveraging dynamic programming and limiting the range of positions we consider, achieving optimal performance for the given constraints. In this first example, we are given 3 steps to take and an array length of 2. This means the array consists of indices 0 and 1. To begin solving, we initialize a variable called maxPos, which determines the furthest index we need to explore. This value is the smaller of two quantities, half the number of steps, which is 3 divided by 2, and the highest valid index in the array, which is 1. Thus, maxPos is set to 1, meaning we'll only consider positions 0 and 1 during our calculations. We then initialize a dynamic programming array, DP, with the starting state, 1, 0. This means there is initially one way to be at index 0 and 0 ways to be at index 1 since we are starting at index 0 by default. Now, for the first step, we create a new array, new_DP, initialized to 0, 0, to store the number of ways to reach each position after this step. Starting with position 0, we can either stay at 0 or move right to 1. Staying at position 0 adds 1 to new_DP, 0, and moving to position 1 adds 1 to new_DP, 1. For position 1, we can either stay at 1 or move left to 0. Staying at position 1 adds 1 to new_DP, 1, and moving to position 0 adds 1 to new_DP, 0. After all calculations, we update DP to 1, 1, indicating one way to be at each position after the first step. Repeating the same process for the second step, we again create a new_DP initialized to 0, 0. For position 0, staying at 0 adds 1 to new_DP, 0, and moving right to 1 adds 1 to new_DP, 1. For position 1, staying at 1 adds 1 to new_DP, 1, and moving left to 0 adds 1 to new_DP, 0. After these calculations, DP becomes 2, 2, meaning there are now 2 ways to be at each position after 2 steps. For the third step, we again start with a new_DP initialized to 0, 0. At position 0, staying at 0 adds 2 to new_DP, 0, and moving right to 1 adds 2 to new_DP, 1. At position 1, staying at 1 adds 2 to new_DP, 1, and moving left to 0 adds 2 to new_DP, 0. This gives us final DP values of 4, 4, indicating there are 4 ways to be at each position after 3 steps. Finally, since we are interested in the number of ways to end at index 0, we look at DP 0, which is 4. This means there are 4 ways to stay in the same place, index 0, after 3 steps. In the second example, we now have 4 steps to take and an array length of 3. This means the array consists of indices 0, 1, and 2. As before, we calculate maxPos to determine the furthest index we need to explore. This is the smaller of half the number of steps, which is 4 divided by 2, and the highest valid index in the array, which is 2. Thus, maxPos is set to 2, meaning we'll only consider positions 0, 1, and 2 during our calculations. We initialize the DP array to 1, 0, 0, which means there is one way to start at index 0 and 0 ways to start at indices 1 and 2. For the first step, we create a new _dp array initialized to 0, 0, 0. At position 0, staying at 0 adds 1 to new _dp, 0, and moving right to 1 adds 1 to new _dp, 1. At position 1, staying at 1 adds the value of dp, 1, to new _dp, 1, moving left to 0 adds dp, 1, to new _dp, 0, and moving right to 2 adds dp, 1, to new _dp, 2. At position 2, staying at 2 adds dp, 2, to new _dp, 2, and moving left to 1 adds dp, 2, to new _dp, 1. After updating dp based on these calculations, dp becomes 1, 1, 0. The process for steps 2 and 3 involves similar calculations, updating dp at each step. After the fourth step, the final dp array becomes 6, 8, 4, which represents the number of ways to be at each position after all 4 steps. At the end of the second example, we are interested in the number of ways to end at index 0. From the final dp array, we see that dp, 0, equals 6. This means there are 6 ways to stay in the same place, index 0, after 4 steps. By limiting our exploration to indices within MaxPos and using dynamic programming to track the number of ways to reach each position, we efficiently solved the problem for both examples. To analyze the time complexity of our solution, let's start with the outer loop. This loop iterates for the total number of steps, so the number of iterations is directly proportional to steps. Next, within the outer loop, we have an inner loop that processes positions from 0 to MaxPos. The value of MaxPos is determined by the smaller of two values, steps ///2 and arrlen1. This ensures that we don't simulate positions beyond the bounds of the array. In the worst-case scenario, MaxPos can be as large as steps //2, since we can't move more than half the total steps in one direction. At each position, we evaluate up to 3 operations, staying in place, moving left, or moving right. Each of these operations is constant time, or O1. Combining all these factors, the time complexity is calculated as O steps for the outer loop, O MaxPos for the inner loop, and O1 for the operations at each position. Multiplying these together gives a total time complexity of O steps *MaxPos. In the worst-case scenario, where MaxPos equals steps //2, the time complexity simplifies further. Substituting MaxPos equals steps //2 into our earlier calculation, we get O steps *steps/2, which simplifies to O steps ⁻2. Now, let's consider the space complexity. The primary contributors to space usage are the dynamic programming arrays, dp and new _dp. These arrays are used to store the number of ways to reach each position for the current and next steps. Each array has a size of MaxPos plus 1, which is determined by the same MaxPos value we used for time complexity. Thus, the space required for these arrays is O MaxPos. Apart from the arrays, we also use a small number of additional variables, like mod and MaxPos, which take constant space, or O1. Since the dp arrays dominate the space usage, the overall space complexity is O MaxPos. In the worst case, where MaxPos equals steps //2, the space complexity becomes O steps. Now, let's compare this optimized approach to a brute force solution. A naive method would involve recursively simulating all possible paths for the given number of steps and counting the number of ways to stay at position 0. Since there are 3 choices for each step, stay, move left, or move right, the total number of paths grows exponentially with the number of steps. This results in a time complexity of O 3 steps. Additionally, due to the recursion stack, the space complexity is O steps. In contrast, the optimized solution uses dynamic programming to avoid redundant computations by reusing previously calculated results. This reduces the time complexity from O 3 steps to O steps ⁻2, and the space complexity from O steps to O steps as well, thanks to the use of iterative dp arrays. Whether we consider the best, average, or worst-case scenarios, the optimized approach maintains a time complexity of O steps *MaxPos. In the worst case, when arrlen is very large and steps dominates, MaxPos becomes steps //2, leading to a final time complexity of O steps ⁻2, and a space complexity of O steps. To solidify our understanding, let's mathematically prove the big O complexity. The outer loop runs 4 steps iterations, while the inner loop runs up to max pos times for each iteration. Within this inner loop, each position involves constant time operations, O1. This leads to an overall time complexity of O steps * max pos. Substituting the worst case value of max pos equals steps ///2, the time complexity becomes O steps *steps/2, which simplifies to O steps ⁻2. On the space side, the dominant factor is the size of the DP arrays, which is O max pos. In the worst case, this becomes O steps. The key takeaways are that the optimized approach reduces time complexity from an exponential O 3 steps to a polynomial O steps ⁻2, while maintaining a linear space complexity of O steps. This efficiency is achieved by carefully limiting the range of positions to min steps //2, rlen1, striking a balance between time and space requirements. When tackling this problem, there are several common mistakes to be aware of. First, overcomplicating the base case can lead to subtle bugs. For example, if you have 0 steps, the only valid position is index 0, so the answer must be 1. Similarly, with 1 step, you can only stay at the starting position or move once, making the base cases straightforward but critical to handle correctly. Another common issue is ignoring movement constraints. Many variations of this problem include boundaries or limits on movement, and forgetting to account for these can result in invalid solutions or even infinite recursion in brute force approaches. Additionally, inefficient recursion without memoization is a frequent pitfall. Naively recalculating the same subproblems leads to exponential time complexity, which is impractical for larger inputs. Always use memoization to store intermediate results and avoid redundant calculations. Lastly, misunderstanding the stay option is a common oversight. Remember that staying in the same position is often a valid step, and omitting it will reduce the total number of valid paths. Your solution must account for all 3 options, moving left, right, and staying in place. Off by 1 errors are another frequent source of bugs, particularly when working with arrays or dynamic programming tables. It's easy to accidentally access out-of-bounds indices when handling boundaries, so always double-check that your indexing aligns with the problem's constraints. Now, let's consider how this problem appears in interviews. Recognizing key patterns can simplify your approach. For instance, this problem shares similarities with dynamic programming questions like grid traversal or Fibonacci sequences. Identifying these patterns can help you reduce the problem to a well-known structure. The optimal approach typically involves using dynamic programming with a state representation like dp, I, j, where I is the current step and j is the position. This ensures an efficient O, n*k, time complexity, where n is the number of steps and k is the maximum reachable position. For further optimization, you can reduce space complexity from O, n*k, to O, k, by storing only the results from the previous step instead of maintaining the entire dp table. Finally, during interviews, always clarify the problem's rules. For instance, ask what happens if you step outside the boundary. This ensures you don't waste time on invalid assumptions or edge cases. This problem is closely related to several other dynamic programming problems, which can serve as great practice. For example, LeetCode 70, climbing stairs, is a classic Fibonacci-style problem with a similar structure. LeetCode 62, unique paths, focuses on counting paths in a grid, another foundational DP concept. LeetCode 198, House Robber, highlights optimal substructure and overlapping subproblems, which are also central to this problem. Finally, LeetCode 935, Night Dialer, involves movement constraints and path counting on a keypad, making it a more advanced variation. Understanding these problems will not only reinforce your dynamic programming skills but also help you recognize recurring patterns. Now, when it comes to potential approaches, the brute force recursive method is the most straightforward to understand. Here, you explore all possible paths recursively. However, this approach is highly inefficient, with a time complexity of O, 3 to the power of n, making it impractical for larger inputs. While simple to implement, it's only suitable for very small cases or for understanding the problem structure. The dynamic programming approach significantly improves efficiency by using a table to store the number of ways to reach each position at each step. This reduces the time complexity to O and *k, making it much more scalable. However, it does require O and *k space and less optimized. To address the space usage, you can use a space-optimized DP approach. By storing only the results from the previous step, you can reduce the space complexity to O, k. While this approach is a bit harder to implement, the trade-off in memory savings can be substantial, especially for larger inputs. Another advanced but highly efficient technique is matrix exponentiation. Here, you represent transitions as a matrix and use matrix exponentiation to compute results efficiently. This method achieves a time complexity of O, k cubed log n, making it extremely fast for large inputs. However, it requires a solid understanding of linear algebra and can be harder to debug during interviews. Each of these methods has its own trade-offs, so it's important to choose the one that balances efficiency, complexity, and the constraints of the specific problem you're solving. Thank you for joining. Today, we tackled problem number 1269 and explored how dynamic programming can optimize solutions for problems like these. Remember to practice regularly and review concepts like recursion, base cases, and constraint handling. See you in the next session, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!